So now we're going to get into some further discussions about how the electrons are arranged in the atom. So the J.J. Thompson, the same person who devised the method of determining the mass-to-charge ratio, he came up with a model for the atom. And according to his model, the atom consists of electrons equally spaced within a positively charged sphere. So the electrons will be spaced equally inside that particular sphere. Now, let me just say that they are already known that the atom is neutral, and because part of the atom consists of electrons, then it stands to reason that the other part will be positively charged, right? And the protons were not yet discovered, which is responsible for the positive part of the atom, but the conclusion was arrived at that, well, if the atom is neutral and the electrons are negatively charged, that means that there's some part of it which must be positively charged. So what J.J. Thompson thought, or his idea of the atom, is that the positive part is a large sphere and the electrons are equally spaced within that sphere. All right? So his proposal for the hydrogen atom, for example, is that there's only one electron, and that electron will be in the exact center of the sphere. All right? So that's his idea of what the hydrogen atom looks like. And then in the case of the helium atom that has two electrons, those two electrons will exist along a straight line along the diameter or along a line through the center, and each electron is halfway spaced between the center and the outer surface of the sphere. So in other words, according to J.J. Thompson, this is basically the representation of the helium atom. You have the two electrons embedded, equally spaced in a large nucleus, all right, which is positively charged. So that's basically the helium atom according to the J.J. Thompson model, which, by the way, is also called the raisin pudding model, all right? And according to J.J. Thompson, if you were to remove one of these electrons from this model, then the other electron will simply go to the center of the nucleus, and that would be the structure of the helium plus ion, all right? So that's basically the idea that J.J. Thompson came up with in terms of how the electrons are arranged in the atom in relation to the positive part of the atom. So, of course, in science, when somebody comes up with a model or a theory, then other scientists, or even the same scientists, will try to test that model. And that is exactly what happened. Another guy by the name of Rutherford, he came up with an experimental setup which was designed clearly to test this particular idea. So let me explain what is happening in this setup right here. This consists of a metal foil, which is actually gold, a very thin foil. And then over here, we have a source of alpha particles, right? Radium, all right? Radium is a very radioactive element, and it spontaneously emits some particles known as alpha particles. And alpha particles, by the way, are the same as the helium-4 nuclei. All right? So this is the same thing as alpha particles. All right? So as such, particles. As such, alpha particles are obviously positively charged, and they are allowed to shoot from inside this lead shield here along a straight line to hit the gold foil, right? Now, if J.J. Thompson's model was true, then one would expect that because the alpha particles are positively charged, and because most of the atom would be positively charged, then the alpha particles would simply be repelled by the atoms, according to the J.J. Thompson idea, right? What was found, however, was that most of the particles, most of the alpha particles, pass right through the gold foil and can be detected directly on the other side, all right, by this microscope here, okay? So that's basically what was discovered by Rutherford in his experimental setup. Now, in some cases, some of the particles are deflected at an angle. So as can seen by the detector being here, some particles will be deflected at an angle here or here, and pretty much anywhere around the circumference right here. And in some cases, some particles are actually repelled, as indicated by this pathway here. So the detector here would detect those particles, right? So what that tells us is that basically the model put forward by J.J. Thompson was incorrect, because if it were correct that the bulk of the size of the atom is taken up by the nucleus, then these positively charged particles will not pass through the gold foil. They'll be turned back. All right, all of them would be turned back when they come into contact with the atom. All right. So what this seems to indicate, actually, this particular setup indicates, is that the positive part of the atom is actually concentrated in a very small volume at the center of the atom, and that is called the nucleus. All right. In fact, let me just show you a diagram which illustrates why this is the likely conclusion. So here we have our gold atom. Here we have the nucleus. And of course, these blue dots represents the electrons surrounding the nucleus. And of course, the red arrows here shows you the pathway of the alpha particles. And one can see that based on this representation, then you'd expect that most of the alpha particles will pass through the atom and end up on the other side without being deflected. Now, some of them will be deflected because they may come into close proximity to the nucleus, which is positively charged, and be deflected, as seen by the pathway number 3 here, right? And some may be deflected because of the electrons, such as seen by the pathway number 2 here, right? In the case of those particles that are turned around, if you look at pathway number 4, you can see that will happen as a result of the direct impact of the alpha particles with the nucleus directly, and therefore these will be repelled going back in the other direction. All right. So that's basically what Rutherford's model, that's a conclusion he came to based on his experiment. All right. That the nucleus of the atom is a positive part of the atom. All right. And it occupies a relatively small volume compared to the rest of the atom, while the electrons are more spread out and diffuse. All right. And therefore, that's a reason why the alpha particles, for the most part, will pass right through the atom without undergoing any change in direction. All right. So that, of course, is the modification, or actually, one could say the direct contradiction of the model that was put forward by J.J. Thompson. Okay, so this brings us now to the composition of the atom in terms of the different particles, right? So Rutherford was able to determine the actual number of positive nuclear charges that is present in an atom. And these positive charges were carried by particles which are called protons, all right? And this leads us to the introduction of what is known as the atomic number, which by definition is the number of protons in the nucleus of an atom, all right? Now, this experiment that Rutherford done was done in 1909. So I don't remember when the electrons were discovered, but Rutherford's experiment was in 1909. And then sometime later, a good, I would say 23 years later, another person by the name of Chadwick discovered a third particle known as neutrons. Now, the discovery of neutrons came about because it was determined that the mass of the atom could not be accounted for just by the presence of the electrons and protons, right? So there was some suspicion about a third entity existing within the atom, and it was James Chadwick who discovered that third entity known as the neutrons. And the main reason why the neutrons eluded discovery for some time is because the neutrons have no charge. The technology that they had back then was able only to determine the charged particles, protons and electrons. But the neutrons had no charge, and therefore these particles eluded discovery until James Chadwick came up with an experiment, which I won't get into right now, which allowed him to determine the neutrons. And he determined that the neutrons have no charge, as I said before, and also he determined that the neutrons have about the same mass as a proton. All right, so that's basically how those three particles were discovered. Now, I want to spend some time here talking about mass spectrometry, because this is a technique, one, that will become important for those of you who have to do organic chemistry. There's an area called spectroscopy where you'll be dealing with, in part, mass spectrometry. This particular technique is used to separate positive ions into based on their mass to charge ratios, basically. And this illustrates the effect that a magnetic field will have on charged particles, just as it did in the case of electrons. However, in this case, it's dealing with ions, all right? So you can have what is called a mass spectrum, which is a record of the separation of the ions. And this here that you're seeing on the screen is a mass spectrum for Mercury, all right? Where on the y-axis, you have the relative number of atoms, and on the x-axis, you have what is called the mass-to-charge ratio, all right? In the case of Mercury and most other ions, the charge is +1, so therefore these would be numerically equal to the masses of the particular ions. So the way it works is that you convert the particular atoms into a stream of positive ions, and they're allowed to pass into a region which is exposed to a magnetic field. And the effect of the magnetic field is that it will basically deflect the path of the ions. Now, the ions that are lighter in mass will be deflected to a greater extent. So you have the stream of particles, ions coming through here, and the lighter mass ions will take a tighter turn in terms of the pathway deflection, and then the heavier ones will follow a wider turn with a greater radius, and that is true for the other ions as well. So it's based on that effect that the magnetic field have on the ions that they are separated, and then they're allowed to hit the photographic plate, and it will look like this, right? And what each line represents, basically in terms of intensity, is the relative number of ions that would produce that particular line. So based on the intensity of this line here, you'd see that most of the ions will have a mass-to-charge ratio of 202, right? Which means that the Mercury atom with the mass of 202 would be the one that would be the most abundant Mercury atom present. All right, so that's basically it as far as a mass spectrometer is concerned. Okay, we're going to stop here. The next video I'm going to lecture on deals with wave motion, right? And here we're going to see the connection between electromagnetic radiation and the structure of the atom, all right? Until next time.